Okay. You may have several questions, so I'm here to answer these questions. So the first thing is a crystal oscillator for your Arduino Nano. Yeah, your surface mount Arduino 328P microchip. Because group 2 we are supposed to not fabricate but design a PCB for that system. It was a little bit confusing. I know. I just realized I didn't put the PCB design requirement in the tutorial, but I had it here. Wait, where is that one? Tool. Anyway, if you don't have enough time this week, because the due date for homework 2 is next Friday, right? So we still have a 1 week to work on that. I can extend that a little bit, maybe, but you have to get the system to work on the breadboard next Friday. If you need more time on PCB, take another 3 to 4 days to work on that. So the crystal oscillator comes with a Arduino Nano board. Is a bit different from the one you have been using for the deep version. So I just did a quick search. I ordered a lot in the summer. I couldn't tell like if this is exactly the same one I ordered, but it looks pretty similar to this one. It's a surface mount oscillator, and if you just Google it, asking for like the crystal oscillator 60 megahertz being used for Arduino Nano, you can definitely find out the result. This is what I just did. It already has two 15 picofarad capacitors inside. So literally, this guy has a crystal oscillator and two caps. So do not need to connect another extra two caps to the oscillator. So you can shrink the size of the board even more, okay, even further. Okay. And this is tiny. If you look at that nano board, this is really not taking that much footprint. It's a pretty good one. All right, so that's the oscillator we're going to use. And so if you want to, after you program your Arduino Nano board, you know that you don't have to. So the only two things you need to get your 328P microcontroller up to running, which is powered up and grounded, and connect the oscillator's connection to this guy. All right, and that's it. Nothing else. So whatever has been uploaded to the microcontroller will be able to run after you power it up and connect the oscillator to it. That's a bare bone microcontroller. Let's take a look at the data sheet, see what's going on inside. You can see it has 3 terminals. So what are these terminals? VDD ground and wait, no, it's not the one. Let's do this. Arduino Nano schematic. Let's take a look. Gosh, look at the figure. Not this one. Directly download the figure, save the image as something on the desktop. Okay. All right, is that clear? So find out PP6 and PP7 of the 328 microcontroller. and connect the two terminals on two sides to these two pins, and the middle one should be grounded. And powered up, grounded in terms of the microcontroller. So whatever program inside will be able to run. Any questions regarding this? But here's a question. So I ordered a lot of these surface mount 328P chips. Okay, we can decide which one you want to fabricate. Since I will allow you to fabricate another PCB to the end of semester, it can be this one or can be the one after this. Since the ESP32 microcontroller, we are going to design and we have another project which will last for another 3 weeks after this, right? So you can pick up one which you prefer to fabricate another PCB. I have all the components right in the drawer. Whichever you would like to fabricate, just let me know, okay? But you must design the schematic and layout for this for all these tutorials and tasks, but not necessarily to fabricate the PCB. You just fabricate one of them in the 2 projects or one of the 3 projects. So we probably have this one and the ESP32 project for 3 weeks and another one as a final project. So that's what you are expecting for this entire semester. And you are going to fabricate one PCB from these 3 projects, including this one. Okay, just let me know which one you will fabricate. So what I'm thinking is if you decide to fabricate the very last one, you probably don't have enough time to solder the parts to the board and test it. So I will say either this one or the ESP32 one after this. Just pick up one and design the PCB out of it and test it out. Okay. One more thing. So on the quiz on Monday next week, expect something like design the schematic and layout in Eagle PCB for a bare-bone microcontroller. Can be the deep version 320A or can be the surface mount 320A. I will provide a link to the data sheet of the 2 microcontrollers, and you are going to draw the schematic and draw the layout in a pretty short period of time. Okay, since I have 10 problems, right, design, and I know we only have 55 minutes, but I definitely won't let you do like 4 PCB problems. Maybe I will pick up 2 from the 10 problems, one for programming, one for PCB. Okay. So you need to know what are the peripheral interface or connections for the 328 microcontroller. All right, either the 328P deep version or the surface mount version. So look into that. Prepare for that from today to the weekend and for the quiz on Monday. Okay. If you already forgot how to design the devices in Eagle PCB, practice it during the weekend. You haven't, right? Because I hope you guys can, be super familiar with PCB design after this semester, and that's the goal for this semester. And if you are looking into the microcontroller classes, it's actually not called microcontroller. In some of the other institutions, they call it microprocessor. And another application-oriented microcontroller class can be called embedded devices. And we will have all these things covered in this curriculum. So for this class is going to be focused on application. So we are going to do C language programming. And we don't care about the very bottom level architecture of the 328 microchip. Because if you really want to learn that, you have to program in assembly. Okay, so you can see what we are doing here. I assign you a project, for example, detect the temperature and display on the OLED and send it to to the IoT third-party website. So that's the entire project. You can program in C language in 2 weeks, right? Or 3 weeks. Get it done in 3 weeks. You don't need to care about the driver. So the driver means all the library running behind the scene to drive all these bottom level operations of the chip. You just need to use a function, like something and parentheses, and so that function is going to carry all the arguments and get everything done for you. I mean, if you have to program every single library by yourself, it takes 1 semester to do it, probably, just for writing the libraries. And don't mention you get everything done for the project. It's impossible. So if you are doing assembly, I would say you learn all the assembly languages and you'll feel super frustrated. You feel like this is not funny at all. I don't want to pursue a computer engineering degree in the future. I don't even want to work for the company which is doing computer engineering stuff. I'm one of the victims of this kind of education, and this is not making sense at all. I mean, whenever you are in your sophomore year or junior year, you are thinking you want to pursue a degree like this, but you were taught with assembly, and for the entire semester, you put all the efforts towards the end of semester for a final capstone project, but you can only get your microcontroller to control SSD. It takes 4 weeks just to display a number on SSD. You assemble it. Okay, you are not feeling satisfied. This is not great. And also in the real world, you are not going to program assembly to design a product for the company. Not at all. And so you probably want to ask, I mean, why so many people are still learning assembly? So you do need to learn the bottom architecture of the different types of microprocessors. So this is a pretty simple 8-bit microprocessor. We have a class which is going to teach you assembly a lot, and only assembly but nothing else for computer architectures in next semester. So it's going to be CE401 computer architecture. It's going to be an ARM architecture or MIPS. Either one, I think. So Dr. Nishat Majid, so he's going to teach that course. So that will be assembly only. So you will learn some assembly over there, but not here. Okay, we just need to design a project and get a product out of it. That's it. And also, so there are several different layers for computer design, either software or hardware. On the software side, it's more computer science oriented. So people are programming in the desktop. It's actually a more advanced microcontroller or microprocessor, but you are not programming using an IDE. It has a dedicated operating system to run the program to the CPU, which is also a microprocessor in the desktop. You don't need to worry about which pin you are controlling. It just it's a very, very high level programming language. So that's the CS part, okay? And for entry level, which is entry level microprocessor programming, which is whatever we are doing right now, C programming, and never care about the bottom level assembly, but just the C programming language to control the pins, control the I2C, SPI, serial, all these kind of things. So that's the second level. It's not super high, not super low, but in the middle. So, but compared to the C++ you have programmed in Visual Studio. So the C language of the microcontroller is a bit lower level. I'm not saying lower level means simple. I'm just saying just lower level towards the bottom of the hardware. Okay, so lower level language, which is the embedded C language you are learning right now, and below that, below the C language embedded processing, embedded devices programming, which is the hardware description language, FPGAs, it directly program the digital synthesize for the FPGA board, design the logic block and download it to your FPGA, and you are going to learn it in embedded devices in CE433 in the spring, which is another super important course. So yesterday, Dr. Shrikant what's his last name? Judd Huff. Okay, so he came to my office and asked me what we should cover in embedded devices. He was thinking probably, it's kind of like a microprocessor course, and which is gonna lean to the directional assembly. I said no. You guys have to learn FPGA and Verilog. So there are several different things. High-level programming languages, C++, Python in desktop, C programming for embedded devices, microcontrollers, and Verilog, which include digital design and digital verification, like UVM, all the protocols. You are not going to just write a C language really simple like SPI.H, right? No, you are going to care about every single moment in the timing diagram. That's everything about hardware design. So it has to be covered. So it's going to be Verilog and hardware discrete language in embedded devices. And the next level is the very bottom level, pretty much, since you are hand drawing every single transistor in the chip, which will be covered in engineering 338. It's called digital electronics, but it's actually a digital VLSI design. VLSI stands for very large scale integrated circuits. So you are going to hand draw every single transistor and to form digital blocks, and then combine the digital blocks to form a ALU, to form a RAM, memory, all these kind of things, and put them together and into the path frame and create a GDS2 file for fabrication. We're not sure if we can fabricate it, but at least the GDS2 file is ready for fabrication. Okay, so here's the difference between FPGAs and microcontrollers we are using. So if you were in analog electronics last semester, what was the technology we used for layout? Do you remember? Yeah, but I mean the technology which was 500 micron. 500 micron technology, which is 500 nano, right? So 0.5 is half micron as a minimum length, but normally we double it as a minimum. So it's 1 micron transistor. Every single transistor is 1 micron. So we don't have that much space to host billions of transistors. That's like the 5 nanometer technology right now is running your CPU. So it's going to be slow because a huge device has a large capacitance to be driven up and down, charge and discharge. So it has a lot of capacitance, so it won't be able to run that fast. So which means it's going to limit the speed of the oscillation. You cannot oscillate or give a really fast clock like in gigahertz to run your 500 nanometer chip. So people have been saying FPGA is faster than microcontrollers. If you need a really fast data acquisition application or platform, you want to use FPGAs but not microcontrollers. So here's the question: why is that? You guys are computer engineers. Why FPGAs are normally faster than your Arduino chips or other microcontroller chips? I mean, for the very fundamental reason, not the computational and organization and optimization. So do you know what's the technology being used for your 328P chip? Have you ever heard about it, or somewhere around how many nanometers per transistor? It's 350 nanometer. It's huge. And they are trying to optimize it. Sometimes they probably have a newer version which is using 130 nanometer technology, but it's still huge, right? So why they have to use 350 or 130, but not 5, not 20? It's cheaper, way cheaper. That's why you can buy every single 328P chip for less than $1, sometimes $2. As every single microcontroller is only like $1 or something. So that's one of the main reasons. Another reason is your microcontroller has ADCs. So it's a mixed signal integrated circuit. It's not a pure digital circuit. So which means if you need a reliable analog circuit design, you cannot use 5 nanometer or 10 nanometer technology. So it's limited to, I think, somewhere around 90 nanometer. So anything lower than 90 nanometer will be not reliable for analog design. So it's not able to give you a reliable results to handle all these sine waves and analog signals from the outside world. So what are the components are doing analog thing inside your microcontroller? What's the part inside? What's the block, function block in the microcontroller is dealing with analog signal? ADCs, your analog input, right? So there's a couple of ADCs inside being connected to the A ports, analog ports, and ADCs have a lot of op-amps inside. Do you still remember the size of the op-amps in your chip? It's not small. We made it pretty large, but the people in the company can make it smaller compared to our 500 nanometer op-amp, but it's still large. Whenever it's dealing with analog, it cannot be small. So it's huge actually compared to the size of the pad. So because of that, you want to sell in terms of, so from the side of the company, they want to sell microcontrollers to people like us. We need just one microcontroller can do ADC, right? So have an ADC on the chip, so you can detect analog inputs whenever you have a potentiometer is detecting all these signals, and you don't want to use another dedicated ADC outside of the chip. It's just causing more problems, and you have to have another chip being placed on the board. It's taking more space, right? So it's just one microcontroller can do everything. So it has to use a larger technology in order to integrate all the different functions in one chip. So it has to be huge, and which limits the speed of the microcontroller. Imagine that you are having 350 nanometer transistors on the chip. It cannot run super fast. But FPGAs, it only has logic blocks, logic gates, but not analog parts, right? Normally, so that all the commercial FPGAs on the market, they have an array of gates. So just program it, and then they will connect the gates to the specific grid points in the FPGA. Digital only. So a lot of digital boards, they are fabricated in 20 nanometer technology. That's why FPGAs are way faster than your microcontrollers. 328, you compare 20 nanometer to 350 nanometer, right? So you can tell which will be faster, right? So after microcontroller programming, you got to learn FPGA, you got to learn Verilog. That's a must, okay? And after that, the very bottom level will be cadence. Use cadence to design IC chips in digital, analog, either way, but you have to learn that. So that's pretty much everything from the top to the bottom. That's why, if I go back to 15 years ago, when I was in college, if I had to pick up another major, I'm going to find a good institution which is teaching me computer engineering, but not something else. Okay, I know computer science is important. I know programming is important, but I can learn programming in computer engineering programs as well. But something else people couldn't learn in computer science programs, which is microcontrollers, FPGAs, and cadence. Okay. So you guys will be more, versatile, and your skill set will be more complete. You can, if you hate it, no matter, doesn't matter, it's because you have been trained in programming in software, C++, Python, algorithms. You can still find a coding company just do coding, which is fine. If you want to go to some companies like Qualcomm, Samsung, Apple, who are dealing with a lot of digital hardware design, which is fine too. So you can send your applications to so many different companies after you graduate. All right. Okay, so make sure you know how to lay out or design schematic or lay out the layout, design the layout of the bare bone microcontroller for the surface mount and the deep version as well. Expect something like this in the quiz on Monday. Okay, and the programming problem will be super simple. It won't be complicated at least. So I will just, for example, I will show you a pattern of data output in the serial monitor and just let you program something to realize to implement that display in the serial monitor. Okay, or program some implement some interrupt to detect temperature from some resistor and display onto the 4-digit SSD and anything you can imagine of things like that. So you have worked on these kind of problems right now or in the past. Um, and I know we only have 55 minutes, so I will probably just put one programming problem and one PCB layout problem on the quiz. Any questions? No? Yeah, just refer to the email. I sent you an email yesterday. So I was thinking to give you an example pool, but I just realized, for example, the PCB layout examples, if you work on that during the weekend, so just directly open up and make a snapshot during the quiz, then you are done. You don't need to work on anything during the quiz, which is not fair to other people. So I would just let you know what are they can be in the bigger picture. You don't have to know the specific ones, but just let you know, there will be something regarding Eagle PCB schematic design layout. Okay. Okay, that's for the quiz and for something else in general. And now for homework 2. I know you guys are struggling. I don't know if that's the correct words to say, a little bit sometimes. But let's take a look at the tutorial. I would say for the first half, not first half, first 80 points. So until here, until task 3, all the sketch has been provided on the tutorial. So if you want to get 80 points from this tutorial, go ahead and make all the hardware connections and upload the code to the master and slave separately and demonstrate you can show this on ThinkSpeak. 80 points. Not even PCB design. No, not there yet. So everything on the breadboard to here, 80 points. So 80 points is B minus, right? So if you can convert whatever here showing in the video to the PCB layout and schematic, another 10 points. So if you couldn't do the customizable AP adjustment for the system, which is A minus, 90 points, which is A minus. If you can do it, I'm pretty sure that will be A, right? Over 93. That making sense? If you're saying you really couldn't do the customizable AP, the username and password for the program, just connect everything on the breadboard and demonstrate you can show the temperature on ThinkSpeak and convert everything to a PCB design. Okay, everything. So what I mean here is you cannot use a nano board to do that. Okay, you have to use a bare bone microcontroller with the oscillator on the PCB. So it's going to be two microcontroller, 322, no, 380, 328 MCUs, a surface mount with 2 oscillators on the PCB and power supply as well. So you need to use a 1117, right, 5 volts regulator. Imagine it's going to be powered up by a jack header So jack header is adapter used in a lab for the PCB, power PCB testing, right? Remember that's the 12 volts output DC. So you need a 117 regulator, 5 volts, to convert that 12 volts into a 5 volts DC to power up your 320A microcontroller. Okay, so your 320A microcontroller is a 5 volts logic, not 3.3. All right. Yeah, so this remind me. 3.3 for, yeah, for ESP. Exactly. Yeah, you're right. Okay, yeah, that's right. So you need a 3.3 to convert that 5 volts to 3.3, and that 3.3 is powering up your ESP module. And you don't want to use the 3.3 from the microcontroller to drive this guy, because this guy arguably is taking something close to 1 amp. That's a 1 amp module. But when I was testing, it's not going to 1 amp. It's like a couple hundred milliamps. So I forgot what's the maximum current flow the 328 chip can handle. I think somewhere around 400 milliamps, 200, 400 milliamps. All right, so definitely don't want to use that one, the 3.3 volts from that microcontroller to drive this guy. All right, so we need the 2 regulators, 5 volts and 3.3 volts. And so bare-bone microcontroller from the Nano, but not bare-bone for the ESP. And I'm not expecting you to design the PCB antenna like this, right? You're not doing that. So directly just design a header, pin header, for so you can plug in this one to there. Just 8 holes, 2 columns, 8 holes. So you can insert the female header to the PCB. So you can then after that you insert plug in your ESP to that female pin header afterwards. All right, you are not going to separate anything from this module. So directly just use the module. That's a $2 Wi-Fi module. Just directly use it. Any other questions? For testing purpose, so just through holes. So you have a PCB comes with through holes. When you're testing, I would recommend you have, I think that's fine actually. Doesn't matter since you have an air blower. If you see something going wrong, you can still desolder it, just use an air blower to blow it. Yeah, just design 3 through holes. So you can choose to either solder a pin header to it or directly solder the sensor to it. But I think after you received your PCB board at the first time, I would use pin headers first, because just in case the board is not working properly, I probably need another design in the future. So just solder pin headers to it, so you are not wasting any of the sensors. The sensor is more expensive than the header, right? So sensors, I think the DSP, not really too expensive, but $2 for each, I guess. Not too bad. But you can solder a pin header to there first for the testing purpose. Okay. Same for the same for the OLED as well. Huh? No, surface mount. Yeah. This guy. This one. Here. I'll send you a link of this part from DigiKey. So I'll show you the one I ordered, so you can directly use that. Yeah, I think I ordered like a couple hundred of these ones in the summer. And you didn't pay the course fee, did you? Does this course have a course fee? I told you, right? Because I forgot to propose it last year. Yeah, never mind. Yeah, which one? Yeah, I know, I understand that. So let's take a look. So this is not a code for that part, okay? So the first thing I want to let you know, which is a push button detection. I'm pretty sure you have done that already since you use it for robotics too, but for other people only. So for push button detection, it's doing a rising edge detection. So you can have a push button, and so it's going to be something like this, I guess. That's a pull-up resistor, and that's a push button here, and that's a pin to the digital IOs of the Arduino board. So what's the value of the pull-up resistor? What's the resistance? What's the resistance of the pull-up resistor normally? Huh? Yeah, 5 or 10K is good. Yeah, 1K is too small. 100K is a bit too large, so 10K normally. So wait, it's going to give you a high. So this is not good design actually. Let's think about it. Here's the push button. Here's a pin, go to the digital input of the microcontroller. So what is this? What is that? Pull down resistor. That's a pull down resistor. You're saying, are you just making it up? I'm not. So it is a pull down resistor. Why is pulling down the pin? Because before push the push button, it is pulling pin D down to the ground, is it? So what's the resistance of that resistor? Still 10K. Okay. So if I do not push it, what's the value here for D? What's the voltage for D? 0, because no current, no voltage drop. 0 volts here, 0 volts here. Okay. So whenever someone push it, it's going to short this pin to the VCC. All right, Taylor asked a really good question. So what's the difference between VCC, VSS, VDD, and the VEE? Let's let me type it here. So VDD, VCC, VSS, VEE. What are they? Sometimes you'll see VDD. Sometimes you'll see VCC. Okay, so D stands for, that's a drain, and C is a collector, and S is a source, and E is emitter. So when you are in the logic class or in analog, when you are drawing all these circuits using CMOS transistors, remember normally I will draw use a voltage module and provide a 5 volts to the power supply, to the drain of the CMOS transistors. So normally I will name the power supply as VDD or VCC. I still remember that. VDD, because that's a drain voltage, and because we are using CMOS transistors, so drain should be powered up. Okay. trying to be cute. Sorry, I don't know. Actually, I don't know. Want to differentiate between the power and the voltage of other pins, probably. Oh, okay. Okay. So the voltage from D2, no, maybe, I don't know. That's less important though. We can take a look in the future. So VDD for the drain, VSS for the source. So the CMOS transistors has a source, right? So normally VSS should be connected to the lowest potential of the circuit. And if you see VSS, you're expecting to connect it to, if you have a negative voltage like -5, -9, just connect to -9 or -5 or ground, okay? Doesn't matter. I mean, depends on the application of the circuit, but it's definitely not the highest voltage, right? So power, so the power should be, or the positive voltages should be shorted to the drain or the collector. So collector is the counterpart of the drain in the BJT transistors, which we didn't get a chance to cover in analog due to the pandemic. So the BJT transistors has 3 terminals, which are collector, emitter, and base. So in the middle is base, but in CMOS it's gate. Doesn't matter, but so it's going to be VDD and VCC for the power, but VSS and VE for the ground or the native voltage source. Okay, so if you see VCC, which means the integrated circuits are based on BJT transistors, not CMOS. If you see VDD, which means inside that pin, that's a drain. So the CMOS based circuit. Okay. If you keep this not being pushed, then sending a voltage 0 to the digital input of the microcontroller, and you are reading zeros from that pin. Whenever somebody push it, there will be a rising edge or a oscillation. Pretty much it's going to be oscillation because of mechanical vibration of the push button, right? It won't be perfect because it happens really slowly. So you need a debouncing circuit, but you can debounce it in software as well. But here we are just detecting the rising edge. So you know somebody just pushed it. Do you want to just write a code like, if it is high, then it's pushed? So why that wouldn't work? So for this pin, right, you have a digital rate assigned to a variable, and you do an if statement. So if that variable is high, then it's pushed. Why is this not working? Yeah, because this code, right, the if statement is running really quickly. So it's going to be executed for like millions of times per second. Just keep checking. I mean, when somebody push it, you think, you can push it really quickly, but after that single push, probably the program has detected that single pin for thousands of times. It's going to detect thousands of highs. So you don't want to detect the high, and you want to detect the change only. Is that making sense? So only a rising edge after the low, after digital low. If there's a rising edge, I don't care how long it's going to last and how many oscillations after it, doesn't matter. If I detect a rising edge, I know somebody pushed it. Okay? So the code has to be, or can be at least, something like this. You can see it couldn't. I can zoom in here. So just put in another So this piece of code is from somewhere else. But we only look at the push button detection part. So wait, is that correct? There are two equivalent ones, I guess. Let me look at what's going on here. Copy, delete, paste. Okay. So you need a variable to hold the last state of the push of the pin, digital pin. And whenever you see a difference, which is being judged by this line, because this is being executed really quickly, right? You know this is running really quickly in megahertz. Doing this. So if there's no change to the state of the pin, for example, nobody push it, so it's going to be constantly low, right? So this one won't be executed, or won't get into this if statement because it's not satisfying this condition. Because the last state and the current state are the same. It's always low. And whenever this is being detected, which means the change has been detected, and it's changed to high. So in the two requirements here, right, it's changed and also it changed to high. Then you know it's a rising edge. So that's a requirement for the rising edge. Then do something. So it can be a lookup table, and you can make a lookup table after that as an independent function. It can be a lookup table, and you can set up a counter how many times the person pushes the push button. So it's gonna carry this argument into the switch function, and as an index to check which ladder you want to display on the little LCD or OLED display. And if that one is confirmed, you can assign that ladder to an array, which will form the credential for the AP, for the access point of the Wi-Fi. So just comparing, it's going to be a matching program, can be a for loop, and have an index moving from the position location 0 to location whatever in the array, and to see if it matches. So that's something you can use, like a lookup table. And so my printer in my office is a browser printer, and it doesn't have a keypad to type the credential of the Wi-Fi to the printer, but it only has one pin, actually, probably another pin for confirmation. So one pin, you just keep pushing that pin, so it's going to change the letters being displayed on the little LCD monitor. And after you confirm it, it's going to move the cursor to the next one. And you can keep pushing the push button until you find out the correct letter and confirm, then it's going to move to the next one and keep pushing. So after you form the entire username of the AP access point of the router, and you just confirm again, and so it's going to send that array or use that array to replace the original access point being saved in one of the variables in the past, right? Something like that. I understand there might be so many little things to debug, right? But that's a big picture of the program. Give it a shot and let me know how that goes, since I haven't done that before. Just I think it's gonna work, but just really need you guys to spend some time on that. I'm pretty sure for a lot of guys have been working with microcontroller for so long, at least for a year or more than a year. I think it's doable. It's not something super complicated. It's totally not doable at all. I think it's doable. We just need to spend some time on that. we'll see how that goes. If no one can get it done, I probably will change the rules for grading. I don't know. But you guys just don't want to have a discussion privately, right? Just like, let's don't do it. So have a Zoom conference to talk about the strategy. What's that? API host. Oh. Yeah, get the credentials changed first. For the API, probably not. It's not being changed so often because you can think about that. If you sell it to a company, they don't need to change the SysSpeak account. Probably for the entire life for the device. Maybe not. Mm-hmm. But if you want to do that, then just one push button to control everything. It takes like 50 minutes to keep pushing. It's a little bit complicated. Yeah, I would say because this probably won't be changed at all for the entire lifespan of the device. Just in case it needs to be changed or so, I would say the customer can contact the customer service company to help with that. Any other questions? So you received my email regarding the quiz, right? Yesterday. It's open book, open notes, open internet, and it just couldn't communicate in between of you. Just send the email, just don't want to do that. And you can search on the website or on my website or in Google anywhere. If there's a question you think you can find it online, just do it. And also you can copy and paste the examples of code, pieces of code from the any website, any forums, anywhere when you are trying to program your stuff. You can search for the command, the instructions for how to use schematic and how to make schematics and layout in EaglePCB. It's totally up to you. You can do it. Again, so it's going to be there will be one programming problem, one EaglePCB schematic and layout problem, and a couple of other very simple ones like the types and very general questions as well, which you can find online or on my website easily. If you are doing this quiz somewhere else, make sure that their computer has a Arduino IDE and EaglePCB, I hope. And also you need have your smartphone with you. So when you are recording the demonstration video of the programming problem, take a really short video and upload to YouTube and copy and paste that link into your submission, which is going to be a PDF file, but converted from a Word file. So you open up a Word file, right? So copy and paste your code in there and your answers in there, and also the links to the YouTube demonstration videos in there as well. Does anyone doesn't have a smartphone or should be fine? Just let me know if you have any issues with this. It's going to be difficult for me to check everyone's demonstration, and you have to wait for me to look at your stuff, so it's wasting time. So just take a video and upload to YouTube and copy and paste the link to your Word file and convert into PDF. Okay? Make sense? Great. That's it for today.